Good afternoon, everyone. I'm Pedro, and I'll present the work, deep learning for oil production prediction in two-dimensional four-scale geometries and viscosity variant flows. And this is my PhD defense, and I'd like to thank the committee for your time. I appreciate it. And well, this work is about the prediction of properties in porous media, considering the pore scale. Porous media appears in a wide variety of applications. Some of them are man-made, others are naturally occurring. And here I'm inspired by the oil industry. And oil reservoirs, they're wide and they're deep, so they take several kilometers. They're in the macro scale. However, the flow phenomena occurs in the micro scale. So the micro scale, also known as pore scale, is where the flow behavior is dictated. So when we change the distributions of the solid grains in the pore scale, the behavior or the dynamics of the flow will change as well. And therefore, the micro scale is very important to the flow, even when we consider the macro scale. And when reservoir engineers, they're interested in managing those reservoirs, well, it's important to know what's happening in the micro scale, but they cannot consider all the detail of the micro scale, so they need to use more general equations with general coefficients, and those general coefficients, they have statistical properties that will show how the flow will behave. Here I'm showing some curves, the relative variability curves. This is a specific property of porous media, and with that, we can compute for two-phase flow the flow rate given a pressure differential. So, well, speaking of scales, the lowest scale is the pore scale, where the flow phenomena happen. We consider detailed equations such as the Navier-Stokes equations, and we could even add more terms of surface forces that appear in the porous media. As we go up in scale, we need to consider more general equations such as Thesis law. And well, the coefficients and the properties of the porous media that will be used in the Darcy's law. Well, usually they are computed through numerical simulations or experimental tests, and well, usually numerical simulations, they're costly, they take a lot of hours of computational power, and experimental tests, they're also expensive, they take a lot of expensive material, and they're long as well. So in here, I'm proposing the use of machine learning methods that could provide an inference of those properties more cheaply. So getting to a literature review, this is about prediction on pore scale porous media, and the first work that I'm showing here is the work of Vo and colleagues. It was published in 2018, and they used CNNs to estimate absolute permeability in 2D porous media. And well, this work is important because this was the first work that introduced the use of CNNs having as input porous media in pore scale to predict property of the porous media. And following this work, there were the works of Santos, Tembele, Wang, and Sui. They applied CNNs to predict single flow properties, not only single flow properties, but the flow fields as well. So one of the works took a cross-grid simulation and improved the field results using a super resolution technique, and other would estimate the fields, and this estimation will be a good initial guess for the traditional method. Well, I also showed the works of Rabbani and Tebari. They extended CNN methods to predict two-phase flow properties. And in here, I'm trying to extend the works and explore a little bit more about the prediction on two-phase flow on wide-scale porous media. So my objective in here is to develop digital petrophysical models that use machine learning techniques to infer flow properties in porous media, with a particular focus on two-phase flows at the pore scale. And as contributions, well, this work is divided in two different studies. And well, both of them consider viscosity as input. And considering viscosity as input is something interesting because I have a two-phase flow, and when I change the viscosity of one of the fluids, the dynamics of this flow changes as well. So I'm trying to see if the neural networks can get this change in dynamics. In the first study, I do a comparison between CNNs and deep nets as the neural network architecture. In the second study, I do a comparison between Fourier features and Laplace Beltrami vectors as a kernel. And finally, I also play with physics-informed laws to see if that's an improvement or not in my system. So getting to my first study, it's called CNN and DeepNet models to predict oil production by water injection in two-dimensional pore space geometries. And the first thing that I needed to do was to develop a data set. And this is a data set of porous media representations. And those porous media representations were considered to be in two dimensions. And to do that, I considered Voronoi patterns. Those Voronoi patterns, they were randomly generated, considering random numbers. Those random numbers would assign the number of centers in the Voronoi diagram. I would also assign randomly the position of those Voronoi centers. And finally, the thickness of the lines in here, they will be assigned randomly. Well, in this Voronoi pattern, the black lines, they're the voids in porous media where the fluid can flow, and the white region are basically the solid grains. Well, based on the random numbers, I would get lower or higher porosity representations, and my data set was developed with over 2,400 porous media representations, with a porosity range between 14 and 19%. Well, initially, those porous media representations, they were considered to be entirely filled with oil, and water would be injected at its inlet. The inlet is the leftmost part of the figure, and the water would displace the oil. The oil would be extracted at the outlet, the rightmost part of the figure. So my model, my finite momentum model, considers the mass conservation equation, the momentum conservation equations, and the convective mass transport equation. I have as simulation parameters the density of water and the density of oil set as 1,000 kilograms per meter cubed. The viscosity of the water is set as 0.001 pascal second, and the pressure differential is 100 pascal. I have 2,400 pore space geometries as samples. For each pore space geometry, I have 3 different viscosity cases, and this leads to over 7,200 flow samples. Well, 7,200 is basically the 2,400 times 3. So in here, I'm showing the dynamics of the invasion. In the first column, I have my initial configuration with the porous media filled with oil. And as the columns pass by, the dynamics of the invasion evolves. So in the first row, I have my lower viscosity ratio case. In the bottom row, I have the higher viscosity ratio case. And the viscosity ratio is basically the ratio between the viscosity of the oil and the viscosity of the water, or the viscosity of the defending fluid and the invading fluid. So, well, I have three different viscosity ratios, 5, 10, and 20. And well, in here I'm showing the graph of oil recovered by water injected. And as expected, when I have a lower viscosity ratio, I'll have a higher amount of oil recovered. And when I have a higher viscosity ratio, the amount of oil recovered is lower. So those curves are basically what I'm trying to retrieve using the neural networks. So I'll have the porous media representations as input, and my output will be the curves of the amount of oil recovered. So about my proposal, I have a CNN. Well, it was chosen the CNN basically because that's the standard way to deal with image-like inputs. And well, my image-like input is my porous space representation, and my output is the curves that I showed in the last slide. I also have an auxiliary input. This auxiliary input is composed of porosity and viscosity. Porosity was introduced in the first work that I showed in my literature review, and viscosity is something that I'm introducing here right now. I also propose the use of a dipole net. A dipole net is a neural network structure that approximates a function operator, and it's composed of a trunk net and a branch net. My trunk net is the same neural network that I showed in the last slide. And I also have a previous input, basically because I'm predicting this curve recursively. So I have the 5 last points of my curve. I predict the next one and do that over and over until I have the entire curve. And this is how my dipole net works. I'm showing here a workflow of the entire of this work. In the top row, I have the finite element method solution to generate my data set. First, to generate the porous representations using the Voronoi patterns. I do the finite element method solution and compute the volume of oil produced. Well, the image is transformed by the efficient net P7 and then the PCA, and this is my image-like input that's fed into the neural network. And I also have an auxiliary input composed of porosity and viscosity. So how was my neural network trained? I used k-fold cross-validation considering 10 folds. Well, this was done to ensure that the results that I'm showing as metrics, they're robust. So I'm not being I'm not cherry picking my results, and my training set is further split into training validation subsets of 80 and 20% each. Well, upon getting to my results, I'm showing here the prediction of the curves for 2 different samples. This is a sample. Those 2 samples are basically 2 different geometries. And I have here in blue, red, and green the viscosity ratios of 5, 10, and 20. The solid line is the ground truth, the dotted line is the CNN prediction, and the dipole net prediction is the dashed line. And well, we can see by the naked eye that those predictions, they're quite close to what it should be. But speaking of metrics, the last point of my prediction for the entire data set, their error was within 10% error margin for over 70% of my data set samples. And when I compare the performance of the dipole net and the CNN, the dipole net was improvement over the CNN, and their performance, considering the R-squared metric, was improved on about 65%. and showing the results for the entire system, not only those two samples. My mean squared error and the R squared for CNN and DeepNet are shown here in this table. And we can see that performance of the DeepNet is better than the performance of the CNN. I also do extrapolation here. This extrapolation was done because the DeepNet is known to be a good extrapolator, and I'm trying to see if that's the case for my problem here. So, well, this model was designed to work well for the viscosity ratios of 5, 10, and 20, but not outside those points. So I consider the prediction for the viscosity ratios of 7.5 and 15 to see if the prediction is good enough. And surprisingly, well, the error was in the same order of magnitude as the predictions for 5, 10, and 20. So the performance for those cases were good. And this is indication that if you want to do a system that will work well for an interpolation in this viscosity ratio axis. Well, those systems, they're good to do that. And when I'm building the data set to develop the system, I don't need to develop data set that's too densely populated in this axis. And well, when I see the prediction of the viscosity ratio of 15 for this first sample, it looks like the prediction of the CNN is better than the DeepNet one. And well, that's the case in here. But when I see the prediction for the viscosity ratio of 7.5 and both predictions for sample number 2, well, the DeepNet still outperforms the CNN. So I still can say that DeepNet outperforms the CNN. So getting to a time comparison, the average time for the finite element method converge was around 1800 seconds. That's around half an hour. And the prediction of the CNN and DeepNet was under a second. So getting to the conclusions, the proposed systems were able to predict the oil recovery factor under a 10% error margin for about 70% of the dataset samples. The DeepNet models present a 45% improvement in the mean squared error and a 65% improvement in the R squared metric when compared with the traditional CNN models. And finally, the models were able to predict the flow behavior even for viscosity ratio values, not considering the training data set. So getting to the second study. It's called Neural Networks for Two-Phase Flow Boros Media with Varying Viscosity. And in here, I had improved predictions via Laplace filter functions. Well, for this work, I generated only 3 geometries, and those Boros representations, they were generated using a grid, and in this grid, I would place blobs in the middle of that with random values for their radii. Well, with those random values, I would get different geometries, and therefore the flow fields for a geometry would be different as well. And in here, I'm trying to predict the flow fields. So for a given Euclidean coordinate, I should output the velocity fields, the pressure field, and the saturation field for this coordinate. For each geometry, I have a separate network to predict those fields. And in here, well, the flow is defined in the same way as in the previous work, in which I have a geometry initially filled with oil and water would be injected at the inlet to extract the displaced oil at the outlet. So About my model, well, I consider again the mass conservation equation, the moment conservation equation. This moment conservation equation is slightly different. I'm considering the Stokes formulation. This is a quasi-static process. So I had to set the acceleration terms to zero. And my convective mass transport equation here, well, will be a source of trouble. And I'll come back here later. Well, about my simulation parameters, I had the density of water and oil set as 1,000 kilograms per meter cubed. The viscosity of the oil is 0.05 Pascal seconds. The viscosity of the water is between viscosity of the oil over 20 and goes up to 2 times the viscosity of the oil. The pressure differential is 100 Pascal. So in here, I'm showing the initial configuration of a geometry, and it's initially considered to be entirely filled with oil. The oil is represented by the blue color, and as time passes by, water in red invades the geometry. Well, in the first column, I have a higher viscosity case in which the viscosity of the invading fluid has a higher value. And in the second column, I have a lower viscosity case in which the viscosity of the invading fluid has a lower value. On the top row, I have the non-dimensional time of 2,465, and in the bottom row, I have the non-dimensional time of 4,825. Well, in panel B, this is when the invading fluid. I'm showing when the invading fluid of the lower viscosity case percolates the geometry. So the invasion already is already breaking through the geometry. And in panel A, I have the higher viscosity case, and we can see that the dynamics of the flow is in a much earlier place in the evolution of the dynamics. In the bottom row, well, that's when the higher viscosity case percolates, and we can see that for the lower viscosity case, the dynamics of the flow is much more evolved. But what's interesting here is not to see how quick or slow the invasion is, but to see that the percolation point, the distribution of water and oil is different, and therefore I can say that the of the invading fluid. So this was about the problem, and now I'll start to speak about the tools. And well, about the tools, in this work I basically changed kernels and losses. Well, I have a complex geometry, and therefore the the solution of my flow is also complex, and they have oscillations. This is the functions of my flow. They have their frequencies, and it is difficult for neural networks to predict oscillating functions. So usually to deal with that, we apply kernels to transform my input space and make it easier for the neural network to predict those curves. So in here, I used Fourier features as a way to transform my input space. I applied cosine and sine functions into my Euclidean coordinates. And this is something that's established as a way to deal with oscillating functions, especially in the physics-informed neural networks realm. And I also try to use Laplace Beltrami vectors and compare the performance of Fourier features and Laplace Beltrami vectors. Well, Laplace Beltrami vectors, they basically have information about the natural modes of the geometry. And with that, we can we can build the solutions of partial differential equations, and this could make it easier for the neural network to predict the flow fields in a complex geometry as well. So I basically needed to have the mass and stiffness matrix that were computed using the finite element mesh. And then using those matrices, I computed the eigenvectors that would be my kernels. Well, about the losses, in here I'm showing an entire physics informed neural network loss. I have results of three different neural networks. Two of them I consider only data loss, and one of them I consider the entire physics informed neural network. Physics informed loss with data loss, partial differential equation loss, boundary and initial conditions as well. So this is my architecture for my neural networks. I have as inputs the time coordinate, the Euclidean coordinates, the kernel, and the viscosity of the invading fluid. And as outputs, I have the x and y direction velocity fields, the pressure and saturation fields. Well, I have three different neural networks. The FFMLP, FF stands for Fourier features. MLP stands for data loss. Delta MLP, the delta stands for Laplace Beltrán kernel. And again, MLP stands for data loss. And finally, the delta pin, delta stands for Laplace Beltrán kernel. And pin stands for data and physical loss. So about my training in testing, well, the training of my neural networks were considered in 5 different viscosity points for the viscosity of the invading fluid. I had the viscosity of the water as 0.0025, 0.005, 0.05, 0.075, and 0.1 Pascal seconds. And the viscosity points used for testing were the 4 points in the middle of those 5 points. And the metrics that I computed considered those 4 points. So getting to the results, first I'd like to say a little bit about the performance of the neural networks. And well, the Fourier feature MLP had the worst performance of all. Then I had the performance of the delta MLP and the delta pin. And well, the performance of the delta pin when I consider all fields and all viscosities and all geometries, the delta pin was the best performing neural network, but the performance of the delta MLP is not far behind. So I'd say that the use of a delta kernel or a Laplace Beltrán kernel is an improvement over the use of Fourier feature MLP or Fourier feature kernel. But considering the loss, the use of physical informed loss is not so big of an improvement. So in here, I'm showing the saturation fields, and in the next slides, I'll show different fields as well. And for all fields that I'm showing here, I have the configuration of the non-dimensional time of 2,465 and geometry 1 with the viscosity of the invading fluid as 0.0025. And panel A, I have the finite element method, the ground truth. Panel B, I have the prediction of the Fourier feature MLP. We can see that this prediction is noisy, so it's a not good prediction. It should be better. Panel C, I have the delta MLP prediction, and well, it's quite close to what it should be. The prediction, the prediction is quite close to the ground truth. And finally, I have the prediction of delta pin, which has some problems in the transition of the phases, in the transition between the water phase and the oil phase. And that happens basically because I have this convective mass transport equation, which is hyperbolic. And well, it's known in the literature that beings are not good in predicting those kind of equations, basically because they have their sharp gradients. And well, here in this problem specifically, this is a source of trouble, and we could not get hit of this smoothing in the transition of the two phases of the water phase and the water phase. There should be an abrupt transition, but we could not due to the training phase of my neural networks. So I'm showing here the velocity field, the ground truth, then the clear feature MLP prediction. Again, it's noisy. Then it comes the delta MLP prediction and the delta P prediction. They're quite close to each other and they're close to the ground truth as well. I could draw the same conclusions for the y direction field for the velocity as well. And finally, I get into my simplest field. This is the pressure field. It's almost linear. And again, Fourier feature MLP could not predict as good as the delta MLP and delta P. It's clear here in this bottom right node that the intensity of the pressure field should be higher here. So with those inferred fields, I could compute the relative permeability. Well, basically because I only needed the flow rate of oil, flow rate of water, and the total flow rate, and I could compute that by integrating the saturation field and the x direction velocity field. And well, I computed the relative permeability. And in here, I'm showing the metrics of those predicted curves. So for geometry 1, considering the relative permeability of water, the delta P have the best performance. Then the relative permeability of the oil for geometry 1, the delta MLP, well, outperforms delta P. And when I consider geometry 2 and 3, the delta MLP had the best performance overall, and that happens basically because I had to compute the flow rates, and to compute the flow rates, I need to consider the saturation fields, as delta P has this problem in the prediction of the saturation fields. The error is carried over to the computation of the relative permeability. Well, here I'm showing a graph of relative permeability for a specific geometry. And what's interesting here is to see the prediction of the FFMOP for the water relative permeability. And well, clearly it's a very bad solution. And this basically happens because the saturation fields of the FFMOP is noisy, and the FFMOP could not compute the relative permeability. So in terms of time comparison, well, the time that it took to generate a finite element method sample was over 28,000 seconds. That's over 7 hours. The testing time for the neural networks were the same for the 3 different neural networks. It was around 6.8 seconds, and that's expected since I used the same amount of neurons, the same architecture, and the same amount of hidden layers. And as training time, the delta MLP was the quickest one, then comes the FFMLP, and finally, the slowest one is the delta P. And it's important to consider that to the training of those neural networks, I had to have five different samples of the finite element method. So the time of the finite element method should be considered in the training of the neural networks. Getting to the conclusions, the Fourier features MLP had poor performance, indicating that the Fourier features are not well suited to flow prediction in complex geometries. Delta P and Delta P exhibited good performance among the prediction of all fields and geometries. Delta P had the best performance when it comes to compute the permeability curves from the predicted fields. Thank you.